Welcome to what I hope is a quick video talking about the basics of electrophilic addition reactions. So this is the first of a few videos that I hope to make whenever we encounter a new type of reaction, just to give you the ins and outs so that you're ready to think mechanistically as we problem solve in organic chemistry. So let's talk about why. So in electrophilic addition reactions, alkenes and alkynes, double bonds and triple bonds are nucleophilic. This is the reason why all of these reactions happen. So if we compare a single bond versus a double bond versus a triple bond, if we think about how many electrons are between each carbon, for the single bond you have 2 electrons, for the double bond you have 4 electrons, for the triple bond you have 6 electrons. This means that in between those 2 carbon atoms, in an alkene, you have twice as many electrons as you do in an alkane, and in an alkyne, you have 3 times as many electrons. More electrons means that you're more negative, so alkenes are partially negative, and so are alkynes. These aren't formal charges on atoms, but there's just electron density that can be used that's in between those bonds. So electrophilic additions, your nucleophile is an alkene or an alkyne. Second point, electrophilic additions that have a carbocation as an intermediate follow Markovnikov's rule. So one way to phrase Markovnikov's rule is that you form the most stable carbocation. So if we have this alkene and we have the option to make carbocation number 1 or carbocation number 2. Carbon cation number 1 is a secondary carbocation. This carbocation is a primary carbocation. Secondary carbocations are more stable, so your product follows the pathway that originates from this more stable carbocation. And we'll see what this looks like in a mechanism. But you'll see terms like Markovnikov. This is what we mean. You formed a carbocation, and between the 2 places where your alkene can form, again, I'll number them carbon 1 and carbon 2, you form the most stable of the 2. All right, and then the third thing to know up front about electrophilic addition reactions is that how your reaction resolves depends on the reagents that you have. So if you're trying to not memorize, if you're trying to think mechanistically, you'll do your first step, which we'll talk about on our next slide, and then you'll think, okay, what are the pieces that I have, and then how can we resolve the intermediates that we have left over? But there are a lot of different pathways we can follow. You can think of electrophilic addition as a tree where you have many different paths that can follow from this first step, depending on your reagents. So let's think about electrophilic additions. The first step, if we look at the top of the slide for any electrophilic addition, you have your alkene or alkyne as your nucleophile, and it wants to interact with an electrophile. In organic chemistry, we always draw arrows from negative to positive. Nucleophile is someone who has electrons and wants to share. An electrophile is someone who doesn't have as many electrons as they want to and would love to receive some. So if we draw this arrow, we get this carbocation, which is the Markovnikov product, where our electrophile uses the electrons from that double bond and adds, if we zoom in, if I label carbon 1, carbon 2, our electrophile adds to carbon 2, which gives us a carbocation on carbon 1, happens to be secondary, the alternative would have been primary. So this is our Markovnikov carbocation. This is the first step in every electrophilic addition reaction. So now, if we're thinking mechanistically and not memorizing, what do we need to do? Well, first we need to ask a question. Can our electrophile stabilize the carbocation? If it can, it will even before the carbocation is formed. So an example is when we have electrophilic addition with molecular bromine. Okay, each of these bromine atoms have lone pairs. So our arrows for electrophilic addition are the same. The alkene is the nucleophile. we would have to break this bond because bromine can't have, we don't want it to have overvalence. But before we form a carbocation, because bromine has an extra lone pair, this lone pair can satisfy that. So we get these 3-membered ring intermediates. And there are a lot of different ones that you can have. It depends on your reagents. But if your electrophile happens to have a lone pair, instead of just breaking the bond of the electrophile, that lone pair will come and satisfy that carbocation before it can even form. Because this bromine is one atom, it has either both wedges or both dashes on either carbon where the alkene was. So in this case, bromine uses its lone pair to prevent a carbocation from forming. Another example of electrophilic addition that we can see are with peroxy acids, where peroxy acids are a functional group where it's like a carboxylic acid, but there's an extra oxygen in there. But this is an electrophilic addition, so our arrows can be drawn in the same way. Our alkene is our nucleophile. All right, it attacks our electrophile. We then have to break those bonds so we don't have atoms that have more than their full valence, but oxygen has a lone pair, so oxygen will use its lone pair and prevent that cation from ever forming. And so here we get an epoxide, okay? And then we get our other byproducts. So in this case, oxygen uses its lone pair to prevent a carbocation from forming. And then because we have this acetyl group, depending on the pH of your solution, all right, you could have a proton transfer if you want your neutral epoxide. Another prominent example is for oxymercuration demercuration. The oxymercuration part is this first step of electrophilic addition, where mercury has a lone pair. So if we draw our electrophilic addition arrows, our alkene acts as our nucleophile. We break this bond so that we don't break any full valence rules, and then the lone pair satisfies that other carbon so that a carbocation doesn't have a chance to form. So in this case, mercury uses its lone pairs to prevent a carbocation from forming. All of these have the same arrows, the same first step, but right, we can rationalize that this is a little bit different than using an acid halide because we have a lone pair on our electrophile. So that's the first question you want to ask. After we make our carbocation, do we need to take a step back and say, actually, our electrophile can stabilize this? If our electrophile can't stabilize our carbocation, then we need to ask, can the carbocation rearrange to become more stable? And if the answer is yes, then it will rearrange. So we can draw our electrophilic addition arrows. Our alkene is our nucleophile. It attacks our hydrogen. Hydrogen can only have one bond, so we need to give the electrons to our chlorine. Okay? And in this case, we get this carbocation, which is secondary. But if we perform what's called a 1,2 methyl shift, we call it 1,2 because if we count from our carbocation, one atom, a second atom, there is a substituent there that we can move. So for a methyl shift, we move this whole CH3 and those electrons, and we move them to where the carbocation is. In instances like these, it might be easier to give every carbon a number and then look and match up. So we had carbon 1, we had carbon 2. Carbon 2 is connected to 5 and 6. Carbon 1 was connected to 4. And what happened to 3? 3 used to be connected to 2. Now 3 is connected to 1. Now through this rearrangement, we have a tertiary carbocation, which is more stable than secondary. You can have a 1,2 methyl shift. You can have a 1,2 hydride shift. where it's the same thing except we move a hydrogen and 2 electrons instead of a methyl. We can have a ring expansion, where here we have a 4-membered ring. All right, if we do our first step of our electrophilic addition, we get a secondary carbocation, but we can move this whole alkyl group and expand our ring. Ring opening rearrangements are very common when you have ring strain. 4-membered rings have a lot of ring strain. 3-membered rings also have a lot of ring strain. So if you can rearrange to open a ring to a 5 or 6-membered ring, it is very likely to happen. And then this last one is also a 1,2 hydride shift. However, we go from a secondary carbocation to a secondary carbocation that is stabilized via resonance. If you can stabilize a cation through resonance, it is very, very stable. So even between secondary and secondary with resonance, you can and will see rearrangement. All right, so after we ask those first 2 questions, first, can our electrophile stabilize our cation before it even forms? And 2, if we do form a cation, can we rearrange to make it more stable? Then we resolve our reaction. We resolve our charged species. We try to get rid of our carbocation altogether. And this will vary depending on what reagents you have. So in this first example that I have, I can draw my same electrophilic addition arrows. My alkene is my nucleophile. In this case, my hydrogen is my electrophile. And I generate my carbocation. Hydrogen doesn't have lone pairs. And here we have the Markovnikov carbocation, and there are no other rearrangements to make a more stable cation. So our next step will be using our bromide anion, and resolving. Carbocations are very unstable, so bromine will share its electrons, and now we have a neutrally charged, stable species. To look at another example, all right, we can use our molecular bromine. This one, because bromine has lone pairs, we form our bromonium ion intermediate, that 3-membered ring. But now we have Br-, which still has lone pairs. We can attack and use an SN2 mechanism to give our positively charged bromine a lone pair. So now in our product, everyone is neutral, everyone is stable. And then this example where we have a tertiary carbocation, water can act as a nucleophile. All right, we get our hydronium ion connected to our substrate, but if water is your solvent, you can facilitate a proton transfer and end up with an alcohol. So again, we're just resolving to through different arrows. There are a few different types of arrows each time, but we're following our mechanistic skills from either using SN2 or even just using our arrows from negative to positive to make neutral, stable species. So this is just a quick overview of electrophilic additions. Hopefully, if you just need a place to review or you get stuck, hopefully this is helpful. If you're looking to limit how much you're memorizing, because we have a lot of reactions in organic chemistry, hopefully explaining this type of thinking is helpful. All right, I'll see you in a different video. Bye-bye.